Hi everyone, this is just a reflection video based on our POGIL exercise, the second one that dealt with the Gaussian distribution. Again, I'm posting these to sort of help you guys summarize the take-home message that I hope you all got from this. And again, this is from section 4.1 in your textbook. I recommend you take a look at that, and hopefully things are clear, and if not, we can discuss it more in person or in class. Alright, so we talked about a Gaussian distribution being a representation of a set of measurements. And this came from one of your POGIL questions, and one thing I really wanted to emphasize that the Gaussian distribution, the Gaussian distribution is a representation of a population, right? And it represents a population based on a set of measurements. The set of measurements we call a sample. Okay. So the idea is that we want to take a sample, take a number of measurements based on a sample, and then try to determine something about the overall population based on that. And that will allow us to do a lot of tests and make predictions that we're going to use later in this class. And so, so when we talked about a set of measurements, let's have we refer to this as like a histogram, and so draw this. Right, and for a histogram, the example was number of car seats in cars, and we went through quite a bit of this, and we talked about, you find a bunch of car seats that have 2 seats, a bunch of cars that have 3 seats, etc., say, right? You get generally this sort of bell-shaped sort of looking distribution here. And this is what we could call the histogram. Alright, this is just a different way of representing the data where here we can call this, what we do lots of times is a normalized probability or normalized distribution. Right, and then again this histogram is based off of a sample. Oops. Alright, and so what we said is that we use let's try blue here. We'll use a Gaussian to represent this. That's not a great picture, but this is generally this sort of bell-shaped curve here. We can do a better job of that for you. Okay, try that again. So kind of increases to a maximum and then comes back down like that, right? And this here is your Gaussian. And this Gaussian, right, is representative of a population, right? And so, sort of talk about this population having a mu, which we refer to as the mean. That's right. It's going to be where this is the maximum. And then sigma, which is the standard deviation. And the standard deviation we can think of as being, right, on this side here, right? So this would be your sigma. You have plus sigma, and then you have a negative sigma, because sigma can also be away from a negative value from the mean. All right, and so when it comes to histogram, right, histogram we're dealing with this histogram, we're dealing with a sample. And so for a sample, we have also a mean and a standard deviation. We represent them by this x bar and s. Right. And in your book, sorry, this doesn't look real great over here, but in your book, we'll refer to your book refers to the formula that defines this Gaussian distribution as y. Sorry, it's a little covered up here. But we talked about in the POGIL set, of this being g of x. It's just the same thing. Basically, y here is a function of x, right? And x, each one of these x's refers to your individual measurements, right? So each one of these experimental data points that make up the histogram would be considered one of these x's. And then you have your mu, your mean, your standard deviation. What we saw was that the standard deviation, sorry about that. So the standard deviation and the sigma, the width, are basically inversely proportional. So as your standard deviation increases, the height of it increases. Or sorry, as your mu increases, the height of your mu increases, the width of your Gaussian decreases. Okay, and vice versa. All right, and another thing we mentioned was right, your sample is something that you sort of have to do practically, right? You can't always measure infinite number of samples and get the entire population. So that's why you end up using a number of samples, measurements to make a sample set, which you use for your histograms. And we saw how, like, as you increase the total number of samples here from 6 to 19 to 49 to 125, that the shape of the histogram begins to look a lot more like the Gaussian. So we sort of say as n goes to infinity, right, then our x bar approaches mu, and our s approaches sigma. Sort of looks like an S, it's not a 5. So here, I'll try to make it nicer. So, right, the more samples, the better, right? You get a better representation here. But again, we're dealing with some practicalities of what measurements are really like. In this case, you see this n equals 49. You can see a lot of correlation between that shape of the histogram and the shape of the Gaussian. And so it may be that you don't, taking 125 data points may not give you any added benefit. Okay, so if we have our Gaussian and something like this, sort of, and we integrate that area under the Gaussian. Remember, we said that if you integrate under the entire area of it, you get, it should be 1, right? So we're talking about the integration of this. So if we integrate under the area here, g of x, right, you will get, this will tell you the sum of probabilities under that area. So what I mean by that is, so for example, so this is our mu, let's say, and if we dot down here, it's our mu, and if we look at the area between, let's say this is plus 1 sigma, and this is minus 1 sigma, right? If we integrate the area under that, actually, hold on a second. Right, draw a line down here, right? We integrate the area under that. Let's do a different color here. Do that blue again. Right, you take the area here, and the area here, right? But that area, in this case, right, that is 0.68. Okay, so what that means is, right, the integration from negative sigma to positive sigma for g of x equals 0.6823, right? If we go out even further here to 2 sigma, I'll do green for this one, let's say. So let's say this is 2 sigma here, right? So you got negative 2 sigma, and then positive 2 sigma. All right, and then you integrate that area as well. That integration of that area here is 0.95. Okay, so do the same thing here. In this case, 2 sigma to minus 2 sigma g of x. So what that means is 95 over 6, right? What this means is that approximately 95.46% of your samples of your population is going to be within this range. Okay, so so let's say if we're looking at the example from the cars, where you're looking at car seats, that means that if you're just taking some random car that you're looking at, there's a 95.46% chance that they are going to be within the range of plus and minus sigma of mu. And I believe in our example, I think mu was around 6, and plus or minus sigma was around, or plus sigma was around 1.5. So that would mean that there's a 95% chance that your car seats are going to be between about 3 seats and 9 seats, I think, something like that. So that would make sense. Okay, so basically the idea is that we can use this probability to really understand what's going on with the population. And so the last thing I wanted to mention, this sort of relates to that. This makes a little better picture of the same thing, right? So this is your idealized Gaussian here, right? Here's our mu, right? And you have plus sigma, plus 1 sigma, plus 2 sigma, plus 3 sigma, and that the area under that is represented by these numbers here. And so you can see that, you know, here's where that 68% comes from, because it's plus sigma is 34%, minus sigma is 34%. So you add those two together, and you can expand that out even further. So you can describe all of your population as you expand this out, right? And again, as we expand this out to infinity, we will get to 100%. But you can see, once you get, there's a huge difference between 1 sigma and 2 sigma, but not as much of a difference between 2 sigma and 3 sigma. You see how this is 68% to 95%, and you get from 95% to 99.8%. So it's not as big of a jump. And so this was an example from your textbook where they just showed the same type of thing. In this case, we're talking about lifetime of light bulbs, right? And so this fits, you know, it's a lot larger data set. You can see how nicely this fits the Gaussian distribution. So you'll know, in this case, the average light bulb will last 845 hours, but this standard deviation here, S, is 94.2 hours, and so by our Gaussian distribution here, we know that 68% of your light bulbs will be basically plus or minus 94 hours from this sum here. So hopefully that makes sense to you guys. And so next week, I'm going to follow this up with a video discussing confidence intervals, and then we're going to move on to t-tests next week, which is going to be sections, I believe it's going to be sections 4.2 and 4.3 in your textbook. So I hope you all have a good weekend.